tranquil autumn scene here on the north coast of Sicily. I've come here not so much to enjoy these empty beaches, but to explore a dramatic environmental change, because the Mediterranean hasn't always been like this. To discover this story, we have to go back in time to a period in Earth history called the Messinian. It's only 5 or 6 million years ago. And to tell that story, we're going to use the geology. So we're going to go inland in Sicily, we're going to look at some outcrops, and we're even going to go below ground, because the history of environmental change is recorded in salt mines.
These vast caverns have been cut out from deposits of rock salt, the mineral halite, hundreds of meters thick. And Sicily has a long history of salt mining, though few geologists realised its significance. That all changed with deep-sea scientific drilling. In 1970, the drilling vessel Glomar Challenger entered the Mediterranean. This and subsequent expeditions drilled into the seabed and confirmed the presence of thick salt deposits. This led onboard scientists Ken Shu, Bill Ryan and Maria Biancacita to propose that the Mediterranean had dried out. The salt was mapped seismically under the seabed, the so-called M reflector being its top, and it's better seen on more modern seismic imagery, a thickness of well over 1 kilometre of salt. So extensive salt deposits, and Sicily and its salt lies right in the middle. Now, of course, the Mediterranean is tectonically active, and it's a complex plate boundary, so it's changed shape since the Messinian. But for convenience, we'll retain a modern world view and animate up one of Shu, Ryan and Cheetah's representations. A profile. The modern Mediterranean connected to the Atlantic through the gates of Gibraltar and mixing around the island of Sicily. And here's the salt encountered by the ocean drilling programs. But if the salt on Sicily is representative of the deep Mediterranean, back in the Middle Miocene we need to change to this. Back then the Mediterranean connected east into the former ocean of Tethys. So from this starting point, tectonism closed oceanic gateways. This, coupled with the dry climate, desiccated the basin. So salt accumulates on the dried out seabed. Then as the story developed, global sea level rose and tectonics breaches the gates of Gibraltar. Atlantic seawater pours in and the Mediterranean refills. And the geological record of this is salt, underlain by sediments deposited when the Mediterranean was full of water, and overlain similarly by sediments deposited in deep water. A sandwich with a salty filling. So let's go to Sicily's south coast to see why geologists in the 1970s got so excited about its geological record.
Well, Sicily's always played a pivotal role in understanding the Messinian and the Mediterranean, particularly for outcrops like this. So this is the appropriately named Punta Bianca, and it shows the sandwich of Messinian strata entombed in apparently deep water sediments. These rocks young from left to right, so the youngest rocks are out to sea, and those white rocks are deep water chalks. On the left we've got clays, and these clay stones, which go from Tortonian into Lower Messinian, again are assumed to be deposited in deep water. And then those grey rocks forming those discontinuous exposures running up to the old military thing on the top there, those are the Messinian strata. that are evaporitic. So we have evaporitic rocks encased in two distinct deep water successions. So let's have a look at the evaporites here. And they're mostly carbonates with gypsum preserved as blobs and bits and pieces. So they're what can be called evaporitic carbonates. Really quite a complicated rock. Okay, so let's see what sits on top. So we've come up out of the evaporitic sequence, and these rocks here are younger than the Messinian. They're Pliocene in age, and they continue dipping on out to sea.
These are chalks, apparently deep marine sediments, so the outcrops at Punta Bianca fit this idea, a sample of stratigraphy tectonically dredged up from the depths of the ancestral Mediterranean. Hence the idea that the Messinian geology of Sicily has been elevated. It's a modern island, raised by the tectonics that continues to impact the Mediterranean today. And indeed, the strata of Sicily are deformed, stacked up and thrust onto each other. So there's certainly been tectonism. The salt basins on Sicily, here halite is pink, are deformed, as illustrated by cross-sections through salt mines like Real Monte. Deformed salt, cut by an unconformity, a major feature across the island, formed during the later Messinian, which has been interpreted to imply dramatic, sudden deformation, for some an intramessinian paroxysm. This is the classical view then, developed in the 1970s and indeed still held by many earth scientists researching the Messinian today. A Sicilian sedimentary sandwich, clays underneath, chalk on top, and complex evaporites in the middle. In places, the evaporitic carbonates of the calcare de base passing laterally into thick gypsum, halite, and even potassium salts, a so-called first cycle of evaporites. Above, a second cycle of clastics and gypsum, the two separated by a regional unconformity, a model applied across Sicily with little regard for local structure. But it leaves unanswered questions, especially of how evaporitic sequences hundreds of metres thick could build up. Was there really a tectonic paroxysm that elevated Sicily from abyssal depths on the floor of a once dry Mediterranean? Indeed, was Sicily ever that low-lying? The geology of Sicily challenges these long-established ideas, not least because few modern accounts consider its diverse rock record. So this is an investigation of the Messinian geology of Sicily, using detective work pulling together evidence of basin structure and deformation, along with stratigraphy and the forensics of depositional processes. But this is not a private investigation. Back in the 1990s, I partnered up with Mario Grasso of the University of Catania and, along with our PhD students and colleagues, conducted extensive fieldwork across Sicily. We wrote up our findings and their implications for the Mediterranean. Very sadly, Mario's no longer with us, and so I'm revisiting some classic sites without him. But there's more than outcrop geology. We had unique access to the records of mines, some still active, others abandoned. So Mario and I had access to these spectacular plans of mines with these galleries that showed the various different evaporites, halite, gypsum, through various mines, not only for salt but also abandoned sulphur mines. These, together with borehole information, give fantastic detail on the different evaporites and their stratigraphy, but also the structure of the evaporite basins themselves. You'll see how we use this unique set of data later on in this film, but for now, let's get back to Sicily and head inland to an area rather confusingly called the Caltanissetta Basin, a term applied to a broad area over central Sicily, though, as we'll see, it's not a single basin at all.
So classically, the Messinian evaporites are considered to be the filling in a sandwich of deep water sediments. And if you look over here, there's, if you like, a classic viewpoint. It's a place called Torrente Vacarizzo, and it shows a cliff line of calcare de base, the quote-unquote evaporated carbonates, sitting on mud rocks. So that's the classic setup for the Messinian, deposited on deep water mudstones. Well, if we go to the north of the island, we see it's actually more interesting and more complex than that. Because as we come northwards, we go up into the mountains of northern Sicily. And up there, well, there's more to the pre-Messinian geology than just mud.
This is Shalato, just off the Catania to Palermo motorway, at the foot of the Matanier Mountains.
Buongiorno. So if we look at the outcrop up beyond the pony, you've got the obvious bedding down in there. And the outcrops are red, and you can even see the boulders in them from here. So let's say goodbye to the pony and walk down the track and see if we can see these outcrops in a bit more detail. Stunning. So these are really quite spectacular, aren't they? Really chunky conglomerates. Most of the clasts in here are various limestone units, and they're derived from the local hills. And we'll worry about that a bit more shortly. But they're red, they are poorly sorted. There's a sand layer in here, which if we trace it along, is cut out, scoured out, and then comes back again. So essentially what we're looking at in here is a continental, well, fluvial conglomerate. You can think of it almost forming in a braid plane. So let's see what else we can find in terms of the class in here. Lots of various limestone units in here, but also these things, which are amphibolites, and they're not represented in these hills at all. These represent terrains that lie, or once lay, north of Sicily. So this material's come off the chain and is flooding out through here. Well, let's just get a view from up above, up on the hillsides, look down and see the context for this deposit.
These conglomerates are laterally restricted, penned in by the surrounding hills. They're the fill to a paleo valley.
Okay, so it's essentially an incised valley fill with material coming off the valley walls, but also from further into the hinterland. But the story doesn't end here with these conglomerates. Let's see what they pass up into as they walk up section, and that means walking down the valley.
The modern valley I'm walking down more or less follows the ancient one, though originally the valley flowed in the opposite direction. Here, the conglomerates pass up into channelized beige sandstones.
So we're in a sort of transitional zone between the conglomerates and those sandstones, but it's all that sort of beige, not red colour. And you can see some pretty big sort of dune forms in here coming through like this. Stacks up. So we're in a sort of an estuary, confined delta, if you will, with these sands spilling out southwards into the basin.
So the section at Gelato is an ancient drowned valley. But these rocks are Tortonian in age. They predate the Messinian evaporites.
So for me, these outcrops at Gelato are really important in the story of the Messinian Salinity Crisis, because they tell us that the northern part of the island, just before the Salinity Crisis, was subaerial, continental deposits, but that preceding the evaporite deposition, there was a period of transgression that flooded back over that continental landscape. Maybe just a little bit, but certainly wasn't deep water at the start of the Salinity Crisis, not northern Sicily at least. So let's see how this legacy of continental environments plays out in the northern evaporite basins of Sicily. Fight through the jungle a bit. So, that little tower is called Bordenaro, and it's built on those Messinian carbonates, the calcare de base. But the really critical thing about this site are those sands in the shade below the calcare de base, because they tell you about the conditions, the environmental conditions that preceded the so-called evaporite crisis. So let's go and see what structures those sands contain, which will be great environmental indicators.
The sands are really well sorted and clean, but it's their paleobiology that's key here. These burrows are characteristic of shallow water environments and do not imply anything drastic in terms of salinity yet.
So that's really important. It tells us that this area was in a shallow marine environment. Up north from here, the pre-evaporatic strata include continental deposits. So northern Sicily, at the onset of the salinity crisis, was subaerial or very shallow marine. So let's go and see a salt basin up against the mountains. So up here in the northern part of Sicily here, right at the foot of the Madnia Mountains, and we've still got Messinian strata even this far north. So this cliff line is carbonate, those crumbly rocks at the top, and they're resting on another bench running through there, which are continental red beds, essentially fluvial conglomerates. So Messinian strata there, but that's not really why we've come here. We're going to go around the corner because there's a salt mine down there.
Let's set the scene for the mine. And I've arranged a tour in with my colleague Rosanna Maniscalco and students from the University of Catania. Rosanna was one of Mario's students back in the 90s. And this is all halite, rock salt. Some large single cubic crystals. It's very pure. This layering is simply due to different crystal sizes and structure. So the rock salt is simply boxed up and sold for human consumption. And of course, the packing facility is in an older gallery within the mine. Back to the geology. And the salt is deformed. This is the old cross-section Mario and I put together from the mine plans back in the day. And there are other salt basins in northern Sicily, though they haven't all been developed. There is, however, extensive subsurface information.
That's a rather unlikely place for a prospective salt mine, but that's the Mandre area. So let's look at the geology, the subsurface that was encountered in various prospecting boreholes through there and build up a story.
This is a bit of a grid of boreholes used to define the prospect. A key with the intramessinian unconformity that separates our two evaporitic cycles. Here are the well logs, and we can use them to build a 3D model of the Mandre prospect. Pulling out a cross section, here's the intramessinian unconformity, deformed along with the rest of the basin by folding and thrusting.
So quite a complicated bunch of deformation, and it's associated with a major back thrust that's coming through here and deforming the low ground in there and the basin that lies in the subsurface. So another example of a deformed Messinian basin.
So what have we found out so far? That central and northern Sicily have important accumulations of Messinian salt. That these were not deposited on the floor of a deep Mediterranean, but across an area marginal to the deep sea, that had only recently before been only slightly submerged beneath the waves. And these salt deposits are deformed. And so it's time to look at the structure of the basins that contain the salt and how these relate to the adjacent strata. So here's a cross-section through the so-called Caltanissetta basin. Actually, several basins shunted together, complex structures of deformed syntectonic sedimentary strata. Boreholes reveal something of the subsurface, including thick piles of halite. Two main synclines at Pasquacia and Corvillo. Let's look at a little of this, the Messinian rocks in this, the Sabkha anticline.
So a nice view of the fold structure arching around, picked out by the calcaire bass. It's sitting on that grey material underneath, which is mostly early Messinian, very late Tortonian clay, a unit called the Terra Vecchia. We're a very thin Messinian section coming around that structure.
So let's go and have a look at that unit down at the foot of that slope over there. So This is unfortunately fairly typical of this unit, the calcaire de base. It's a breccia, a collapsed breccia, and it's veined by gypsum. So these are gypsiferous veins that are part of this horrible collapse mess. To see how this breccia forms, because it could form in many ways, we need to go to some other outcrops.
We can get across the northern side of the Corvillo Basin. Rather better bedded units of calcaire de base.
Well, it's very typical of critic fine-grained limestones that they're really hard to see things in the field. But actually, there looks like some structure up in here. So let's go up and have a closer look. So these are preserving a really fine lamination. It's an algal matte texture, but it's got porosity in it, which is sort of filled with sort of sparry fill. So there's something in there that has dissolved away and now being replaced by new calcite. And you can see that texture sort of increases in this direction with the orange staining. Well, that's the new sparry calcite fill. So what this is a classic Sabkha texture, where we have algal matte with evaporite minerals growing in the matte, and later on they've been dissolved away, creating a porosity that then's been filled up by, or is partly filled up by calcite.
Sabkha, an important carbonate evaporite depositional environment named after their type areas on the Gulf Coast of Arabia.
Well, it's likely the evaporite in this case was gypsum, but if we look around here a bit more, we might see evidence of other evaporite minerals. Well, these aren't brilliant examples. I'll just show you what they could look like on ideal outcrops. So you can see these really good rectangle corners, diagnostic of cubic minerals. So what was this stuff? Well, something that's easily dissolved away and was a cubic mineral. Well, the answer is halite. So this limestone once had halite growing in it.
The calcaire de base then, texturally complex but retaining evidence for deposition as a sabkha, and parts that once hosted significant evaporites have collapsed in situ, bed by bed, marked by layers of breccia. Some people call this autobrecciation. Cycles of precipitation within algal matte carbonates, dissolution and collapse. At Sabkha, there's a small stack of these cycles. There are more elsewhere around the flank of Corvillo, up to around 20 metres of calcaire de base. But what about the Corvillo salt basin? Boreholes like this reveal hundreds of metres, chiefly of halite. Let's draw all this at the same scale. Going to the Corvillo basin, a dramatic variation in thickness and facies of the evaporite successions. The Corvillo basin has an exceptional record of evaporation and halite accumulation. But how can such thick successions build up? Starting with a column of average seawater 1 kilometre deep, if this dries out, evaporite minerals precipitate in reverse order of the solubility of their ions. Calcium sulfate first, that's gypsum, followed by halite, that's sodium chloride, and the potassium salts, along with traces of salts of less abundant ions. But how have sections like this built up, with varieties of different salts, including highly soluble magnesium ones? This leaves vast numbers of water column equivalents to have dried out, so we need another way. Here's the model we put together back in the 1990s. It's about the structure, creating mini-basins. Starting at relative high stand and free-ish circulation of seawater, But as levels fall, the outer barrier hosts a Sabkha that acts as a porous pathway for seawater, restricting circulation in and out of the mini-basin. But as the Sabkha develops, it can take out the less soluble ions, leaving more soluble ones to pass through into the mini-basin, where they precipitate the higher order salts, not just halite, but also potassium and even magnesium salts. And because the flux of high salinity water coming through the barrier can continue, thick halite can build up in the basin. So the basin structure defines the location of the different evaporite fascies, and tectonics, the growth of the syncline and the outer rim, along with regional sea level change, will control the cyclicity of the fascies. So understanding here demands interpreting structural geology, stratigraphy and sedimentology. And these structural controls on the stratigraphy extend back to pre-evaporitic times. Let's drop back into the mud and clay of the Terra Vecchia formation. We can return to the northern margin of the Corvillo Basin, the Alamina Ridge.
So amongst all the mud around here, I've come to a place called Landro, and it's a world of carbonates, or at least a layer of carbonates. So this is coral, and pretty much the entire cliff is made of a single species of coral. One of a pair of reef levels that's the latest Tortonian, earliest Messinian in age, that you find in various places in Sicily. But it's not part of the evaporitic sequence, even though it's carbonate. Because here, the first sign of evaporites are in those rocks on the high skyline at the back there. That's the calcare de base. So before the evaporites, we had nice marine water that was able to support a coral reef.
Let's update the mini-basin model. The anticline restricts the sediment flux, so the syncline behind ponds coarser clastics. Mud can get through ahead, but sand remains behind. And then reefs can build up on the crests of the anticlines. And this runs into the evaporitic world when clastic input is turned off. Salt precipitating in the syncline, separated from more or less normal seawater by the porous barrier of calcare de base on the anticline. Back in the day, we took this idea and applied it to the array of thrust-up basins, which the pre-evaporitic strata say formed a bathymetric ladder stepping down into deeper water. And sea level fell across this ladder, desiccating the syncline basins in turn. Halite in the synclines, calcare de base on the anticlines. All the while, a Mediterranean hardly changed in salinity outside those synclines. Only later does the Mediterranean become fully isolated, finally to dry out with salt deposited on the once deep seabed. So the salt basins would be desiccated diachronously, and that's provided the salinity in the mini-basins tracked the sea level fall. But many modern studies assume salt precipitation during the salinity crisis was synchronous between Sicily, other circum-Mediterranean areas and the deep Mediterranean basin. But if that's the case, salinity could not have tracked the regression recorded on Sicily. To have synchronous precipitation across the different levels along our bathymetric ladder, there must be regional hypersaline water, which would charge the upper parts of our ladder and the deep water Mediterranean. Therefore, the Mediterranean at this stage must have been largely still full of, albeit hypersaline, water. If this was the case, its halite accumulated under deep water. But this depiction doesn't fit the fascies we visited on Sicily, nor does it really provide a process for accumulating the evaporitic cycles nor their thicknesses in the mini-basins. Which is why we published our Diachronous model, for Sicily's first cycle evaporites. But our story doesn't end there with a beached Sicilian thrust belt and a dried out Mediterranean. This super low stand, the emergence of the thrust belt, is charted by the intramessinian unconformity, where the deformation that formed the mini-basins, the synclines and the anticlines, continued, but was accompanied now by erosion in a subaerial world. Let's get back down to the south coast. Home to the famous salt mine of Monte. It's a drive-in location and regularly hosts visits by university parties and tourists visiting the ubiquitous shrine to Santa Barbara, the patron saint of miners. The mine walls have spectacular structures in the halite and potash salts. Of course, these are to form first cycle Messinian evaporites, and on the cross section, folds, truncated by the intramessinian unconformity, overlain in turn by the second cycle, and stepping back, the intramessinian unconformity, which is folded. The deformation continued and can be seen at outcrop.
Well, this is a nice spot. So that rather nice fold is cored by the youngest Messinian strata, wrapped by the Truby, the earliest Pliocene strata.
We can drop down to the beach to look at the second cycle strata. They include beds of selenitic gypsum with the characteristic swallowtail form. But chiefly it's clastics, sands like this, but overwhelmingly clays and silts. When interpreted back in the 1970s, these strata were ascribed to a regionally extensive lake, so-called Lago Mare. So let's get back into central Sicily to visit second cycle strata up there. We can head back to the Corvillo Basin and the Alamena Ridge. We were here to see the Landro Reef, but now it's up to the Messinian rocks that lie stratigraphically on top, with the intramessinian unconformity, decorated by local conglomerates overlain by gypsiferous stands. Let's take a look.
So these are intramessinian conglomerates. And we know that because that big white clast up there and others like it are fragments of calcareous bass. So we are reworking first cycle evaporite and its associated sediments as we begin to return to normal bathymetric conditions and flood back over the first cycle rocks.
So let's take this idea further along the Alamena Ridge. It's a location we described back in the 1990s, a site called Balsa Soletta.
So those muddy fields down there are clays of Tortonian, uppermost Tortonian into lower Messinian age. But as we keep going, well, actually get out of the clay. So that left-hand cliff line is the calcareous bass, standing on end, and then it arches over up at the top of the hill, making a fold structure that's dipping down like this, a fold limb. And then as we come over here, we've got all these rocks here which are above an unconformity surface because they onlap the steep rocks of the left-hand outcrop. So that unconformity represents a time period when there was no deposition here, but our originally horizontal calcareous mass was tilted. At that time, sea level dropped spectacularly. It's that period that is thought to date the formation of evaporites in the floor of the Mediterranean. And then later, after that tilting's occurred, we've had renewed deposition on top of our unconformity and our tilted calcareous mass, and then of course more tilting again to get it into its orientation we see today. So a history of tilting and deposition recorded here. Well, that is some pretty spectacular stratigraphy.
So this is the second cycle onlapping unconformably the calcareous mass of the first cycle. And the younger strata form this countryside. Sandstones made of reworked gypsum. But also, like on the south coast, layers of primary selenitic gypsum too. We did our work ages ago, but since then, Rosanna Maniscalco and team have revisited the basin to add substantial sedimentary and stratigraphic data, which show refilling of the Corvello Basin by second cycle strata at the end of the Messinian. And so it's time to pull all this together for Sicily. Deposition of strata in thrust-top basins with continuing steady deformation. Second cycle deposits refilling the basin. And we can represent all this on a chronostratigraphic chart, which plots relative time against place across the section above. Building up stratigraphy, the Tortonian clastics and reefs on anticline crests. Flooded over before evaporitic deposition, the calcareous mass and the halite-rich basin fills, building out as sea level falls, leaving eventually the thrust belt emergent and exposed. Then base level rise and refilling of the basins, before finally the whole lot are blanketed by Truby Formation chalks in the first days of the Pliocene. What does this mean for the Mediterranean? Well, it's a view significantly different to that laid out at the start of this film. Sicily, always high standing relative to the floor of the Mediterranean, so as sea level fell, it accumulated evaporites first, before the deeper basin waters became sufficiently hypersaline to precipitate salt. Diachroneity. Then the Mediterranean refloods, the Lago Mare, covering eventually the Sicilian basins. So when the gates of Gibraltar breached, Atlantic water simply exchanged with Lago Mare. The Mediterranean was largely recharged not by global ocean water, but by Lago Mare water, whatever that might have been. A story then that has pulled on sedimentology and stratigraphy, but also structural geology. And it's the field relationships that are fundamentally important for building stories like this. But what's the Lago Mare? How did the Mediterranean actually refill? Well, that's a story for another film. A sequel coming soon. So thank you for joining me in that journey back in time, exploring the salt on Sicily and its implications for understanding the progression of the Messinian Salinity Crisis in the Mediterranean.